Okay, hello. This is Calc 3 class. I just want to go over last year's test, and hopefully this will be a pretty good review. I based this year's test on last year's test. Some of the problems may be a little bit harder, not really that hard. Please note I did not take any of the questions from our book, so it's not going to be a matter. I mean, you're going to be able to take the test open book, right, because you'll be at home and stuff. But these questions are in the book, so don't spend a half hour looking for them, right? Okay. The ones I did aren't, but they'll be the similar, level of difficulty. Um, okay, so test 4 from spring 2008, apparently. 2018, sorry. And first problem is just evaluating an integral. So one thing on my test, I have you set up integrals versus evaluating integrals. And it seems to me just setting them up is kind of sort of an art in its own, and then actually evaluating is sort of a separate thing. So, read the directions, obviously. Okay. So the first problem, we want to evaluate the integral 0 to the 1 and then 0 to the pi over 2. And the integral is y cosine x dy dx. Okay. So in particular then, how did we learn to do this? You do the inside integral first, and then you move outwards, right? So the inside is with respect to y. So I'm going to have y squared over 2 times cosine x, and I need to remind myself to evaluate, and then dx, okay, from 0 to the pi over 2, and the limits here are 0 to the 1. Okay. So plug in the limits. You can factor out the 1/2. Factoring out constants is always a safe operation, so go ahead and do that. You'll just be left with y squared cosine x, and then we of course evaluate that. And you're substituting in for y. Okay, so it'd be 1 squared times cosine minus 0 squared times cosine, which would just be 1 cosine x. So this would be 1/2 integral of cosine x dx. And then, of course, the antiderivative of cosine is sine, so you get 1/2 sine x evaluated from 0 to the pi over 2. And finally, then, plug in pi over 2 and plug in 0. So the fundamental theorem of calculus. So sine of pi over 2 is 1, and then the sine of 0 is 0. So you're just going to be left with 1/2, okay, which is your answer. Okay, so basically you're just checking to make sure you know how to do a double integral. Problem 2 is sketching the region of integration and then switching the order of integration. Okay, so we have a double integral here going 0 to y, and then what else? 0 to the 4. And inside here we have f of xy, and then we have dx dy. Okay. All right, so first things first, I want you to sketch the region. And when it's dx dy, the sort of orientation is the non-traditional orientation. Okay, so it's your Riemann man is going in that direction, basically. And you think basically curve to curve and then point to point. Okay? So I'm going curve x equals 0 to x equals y. So where did I get that? I got that from the limits on the integral. X equals 0 to x equals y. So x equals 0 is just the y-axis, and then x equals y is the diagonal through the origin. Okay? And then the Riemann man is running on the y-axis from 0 to 4. Okay? 0, 1, 2, 3, 4. And that will be the area underneath that curve. Okay. All right. So now I need to rewrite the integral and put it in the other orientation. Let's put that Riemann man in a different color. Okay. So in that case, then my new integral have order dy dx, and so you're thinking y equals some curve to y equals some other curve. So this curve right here originally is x equals y. You just solve for y, and that's easy to do. Y is just equal to x. Okay, and then the other curve. So think about it. I'm going from this curve to this curve. Okay, so this curve is the y equals x. And then this curve up here is y equals 1, 2, 3, 4. Okay. And then the Riemann man is going from here to here. So it's just going to be the x coordinate of that point. And that point will be where this line and this line intersect, which is 4, 4. Okay. So the Riemann man is running on the x-axis. So that dx means the x-axis basically. And he's running from 0 to 4. Okay. There it is. Okay. And it says in the directions, do not evaluate. So read the directions, please. If you have a question, just send me an email. All right, next, it's problem 3. Sketch the region R of integration and switch the order. So the same problem, and then do not evaluate. So they give us 1 to 10, and then the integral from 0 to ln y, and then it's f of xy dx dy. Right? Okay. So on looking at the sort of the back here, the back end of the integral, this is the non-traditional order. The Riemann man is going up the y-axis, right? Going in that direction. Okay, so curve to curve and then point to point. Curve is x equals 0, which is just the x-axis, to x equals ln y. Okay, so maybe that, what the heck is that, right? X equals ln y. Well, just find, solve this for y, and that it should kind of demystify it a bit, right? So to solve it for y, you exponentiate both sides. You get e to the x equals y. So x equal ln y is just e to the x. Okay? So it's just this curve here. All right. So again, what am I doing? I'm going from y, or rather x equals 0, which is the x-axis, to ln of y, which is this curve. Okay. All right. The Riemann man is running from 1 to 10. So from y equals 1, which is right here, to 10, which will be up here somewhere. Okay. All right, so x equals 0 to ln right here, so that would be this region that we're interested in getting our hands on. Okay, okay. So now I want to change the order of integration. So the Riemann man this time is running in this direction. And you think, you know, now y equals some curve to some curve. So y equals this curve, which we know is e to the x, to y equals this curve right here, which is 10, y equals 10. And then the Riemann man on the x-axis is going from this point 0 to this point here, which is basically the x-coordinate of this intersection point. So to get that intersection point, you just take the intersection of the two curves. So one of the curves is y equals e to the x, and the other curve is y equals 10. Right? So you say e to the x equals 10, and then take the log of both sides, and you end up with x equals ln 10. So at least the x-coordinate, we have that ln 10 comma, and well, we have the y-coordinate is also 10. So this point right here is ln of 10. So I'm going from x equals 0 to x equals ln 10. Okay. All right, let's look at another one. Problem 4. What do we have? Sketch the region R of integration and set up the integral for both orders. Do not evaluate. So this time, instead of having bounds or limits on the integral, we just have a described region. Okay. So the region R is a triangle bounded by y equals 4 minus x, y equals 0, and x equals 0. All right, so I go to my xy plane. 4 minus x, what is that? So its intercept, y-intercept is at 4. Its x-intercept, in other words, where y is 0, will also be 4. So it's this curve. And then y equals 0 is the x-axis, x equals 0 is the y-axis. So we just want to find the integral of x e to the y over this triangle region. Okay, so we have to do both orders. Let's get the traditional ordering out of the way. That would be dy first and then dx. Okay, so in that case, our Riemann man is going in this direction. Okay. So we have curve to curve, y equals 0 to y equals 4 minus x. And then the Riemann man is going on the x-axis from 0 to 4. So I got 0 to 4. Then I need to write it in the other order, x e to the y, and we have dx dy. Right? So the non-traditional orientation, my running man is going in this direction now. It looks like he's walking. So I'm thinking curve to curve and then point to point. Okay, so curve to curve and then point to point. I'm going to have to rewrite this in terms of x. So if you add x over and subtract y, you just get x equals 4 minus y. So a fairly tame example for us. So I'm thinking x equals 0 to x equals 4 minus y. And then on the y-axis, you're moving from 0 to 4. Okay. So pretty simple. Next, let's see, we had 5, it was a little tricky. So sketch the region integration, set up the integral for both orders, do not evaluate. So here's our region R, and then we have xdA. The region is the sector of the circle in the first quadrant bounded by y equals square root 25 minus x squared, then 3x minus 4y, sorry, 3x minus 4y is 0, and then y is 0. Okay, so first quadrant only. This is a circle with, well, a semicircle of radius 5. So in the first quadrant, it'll look like that. This guy, you could solve for y. 3x equals 4y, so y equals 3/4 x. Okay. So it'll have an intercept at 0, and then it's up 3 over 4. Right? So probably looks something like that. I need to figure out this intersection point. Okay, so I could just set this equal to that, and I'll get 3/4 x equals square root 25 minus x squared. Square both sides, you get 9/16 x squared equals 25 minus x squared. Okay. I'm going to add this over, so you get 16 over 16 plus 9 over 16 is 25 over 16 x squares. and over here is 25. Multiply by 16 over 25, and you get x squared is equal to 4. So you get x equals plus or minus 2. Okay? All we need is the positive one because we're just in the first quadrant. So it's going to be 2 comma something. Well, what did I screw up? If I added this to the other side, 16, yeah, it's 25 over 16. And then it seems like I'm screwing something up. Oh, this is 16. I'm sorry. I'm sorry. Yeah, so I was just looking at the picture. There's no way that's at 2, right? So anyways, you need 4. And then to get the other coordinates, we're going to need them both because we're doing both orders of integration. So this coordinate is 4. And then comma, I got to plug in 4 into this equation and get y. Y equals 3/4 times 4 is just 3. Okay, so the point is 4, 3. And we need that because if your Riemann man is going in this direction, and this is the region we're worried about, at first, the top curve is the line, and then second, the semicircle is the top curve. Okay, so you really will have 2 integrals in that case, right? So you have an integral for this region, and then you have an integral for this second region, right? Okay, so let's do that. I'll have this equaling a sum of 2 integrals, and the order is dy dx, and then plus another double integral x dy dx. Okay. So for the first integral, you think curve the curve, right? So it's this x equals 0 to, or rather y equals 0, sorry, to y equals 3/4 x. So I'm going y equals 0 to y equals 3/4 x. Okay. And then the Riemann man is going from 0 to the x coordinate, so 0 to 4. Okay. Then on my next integral, the top curve is now the semicircle, right? So I'm going from y equals 0 to y equals the square root of 25 minus x squared. So y equals 0 to y equals square root 25 minus x squared. And the Riemann man then is going from 4 to the place where the semicircle hits the x-axis, which is going to be at 5. Okay, so I'm going from 4 to 5 there. And then that's the first order. Okay. The second order is a little bit easier, and looking for the right color. So let's put a Riemann man a different color. So he's going in that direction. The bottom curve is the linear curve, and the top curve is the semicircle. We need to put everything in terms of y, right? So I need to solve this for x and solve this for x to get my curve formulas. So solving, firstly, this guy for x, that will give me, well, 3x equals 4y. Divide both sides by 3. X is equal to 4/3 y. Okay. Then you do the same thing for this equation. So you have y equals square root of 25 minus x squared. Square both sides. So you get y squared equals 25 minus x squared. And then add the x squared over, subtract the y squared over, and then take the square root. You end up with x equaling plus or minus square root of 25 minus x squared. We only need this right hemisphere as opposed to the left hemisphere. So the negative of this would be the left hemisphere. I just need this right hemisphere. Okay. Okay, so those are my 2 functions. Right, so in this orientation, curve to curve, the bottom curve is the 4/3 y. So let me get my other integral going. So the other integral is going from 4/3 y to the square root of 25 minus y squared. Okay, so this should be a y. That's not obvious. It looks like an x. Then the Riemann man is running from 0 to the y coordinate of that intersection point, right? And that y coordinate is 3, so that'd be 0 to 3. And then the guts of the integral are the same. X, we just have reversed instead of dy dx, dx dy. Okay, so that one's a little harder. Okay. Conversion to polar coordinates. So the directions are to convert this to polar coordinates, do not evaluate. So in general, there's only really two types of polar curves that generally will come up. Well, maybe three. The first type is usually, I know there's limnosons and there's the rose petals and stuff like that, but usually in the homework, you know, for future homeworks, you're mainly integrating over tops of circles. Okay, so the formulas for those is just for circles centered at the origin, it's just going to be r equals whatever the radius is. So if this point right here is at a comma 0, r equals a would be your polar equation for that. Okay. The other two types then are these kind. One point to note here is that the angle theta is going from 0 to 2 pi, right? Okay, so the formulas for these are either r equals a sine theta or r equals a cosine theta. And it's really 2a if you think of a as a radius value. Okay, but I'll put it in terms of this coordinate here, which instead of a, because a I'm using over here, let's use b. Okay, so this is at b comma 0. So the formula for this guy is always going to be some r equals b cosine theta. Okay? And the thing you got to be careful about when you're doing these is that the rotation is not 0 to 2 pi. The full rotation to get this picture is just 0 to pi. Okay? All right, so that's the one. And then this guy down here, if this point is located at 0b, so in both of these cases, b is the diameter of the circle. If the top point here is 0b, then r will equal that b sine theta. Again, it's traced out going from 0 to pi. Okay, so those are the main types of curves that I would imagine putting on a test. I'm not going to put rose petals or limnosons or whatever else you can imagine. I'm just not that interested. So number 6, then we're converting to polar coordinates. We're going from 0 to the square root of 4 minus x squared. And then we're going from -2 to the 2. And on the inside, I have x dy dx. Okay. Okay. Right. So I gotta convert this. In order to do that, I gotta kind of figure out what this picture is. This is going from y equals 0 to y equals square root of 4 minus x squared. So y equals 0 is just the x-axis. Y equals square root of 4 minus x squared. Well, if you square both sides, you get y squared is 4 minus x squared. And then x squared plus y squared is equal to 4, right? So that's a circle. This in particular is the top semicircle. It's this thing from radius is 2. 1, 2, 1, 2, 1, 2. Okay, so going from y equals 0 to this is y equals 0, and then this is y equals square root 4 minus x squared. The Riemann man, and I'm in the traditional orientation, is running from -2 to the 2. So it's going to be this region that we're integrating over. Okay, okay. So I need to convert that now into a polar integral. So x is automatically r cosine theta. And then to change the dy dx, it'll be r dr d theta. So r times another r will give you r squared, and then dr d theta. The formula for this circle is r equals 2. So remember, when you do kind of the Riemann-Man for a polar curve, it's like this. The Riemann-Man is running around in a circle. So the inner curve is going to be 0, and then the outer curve is going to be whatever this curve is here. Okay? And that curve there is r equals 2. So I'm going from r equals 0 to r equals 2. Then I need the theta value. So theta is going from 0 to pi. Okay, so 0 to pi. And that's the setup. Go on to the next problem, right? All right. Another one of these where you have to convert given the integral. So this is number 7. And I'm going from 0 to the square root of 2x minus x squared. And then I'm going from 0 to 2 on the outer integral, and it's xy dy dx. Okay, so I need to convert. I don't have to evaluate. This thing right here is actually a circle. It's one of the sideways circles, right? So let me get a picture of it. In order to flesh it out, okay, so what do you think? It's y first, right? So it's y equals 0 to y equals square root 2x minus x squared. So it's the x-axis to whatever this is. And what is that? So y equals square root of 2x minus x squared. What is that? Square both sides. Y squared is 2x minus x squared. And then I need to complete the square to kind of figure this thing out. I'm going to move it over first. So I have x squared minus 2x, and then plus complete the square, plus y squared. And on the other side I have 1. Okay. Here I got negative 2, divide by 2 is negative 1. Negative 1 squared is positive 1. And if you add it in there, well, this should have been 0, right? But I'm kind of getting ahead of myself. If you added it on that side, you have to add it on this side. So you have to add in 1 over here. Okay, so on this side, you'll have x minus 1 squared when you factor that, plus y squared, and that equals 1. So it's a circle, radius 1, shifted to the center 1, 0, right? So let's draw that out. The point 1, 0 is right here. It has radius 1. Okay, so it's going to look like this. Okay, and our integral, it's a traditional orientation, so the Riemann-Man is going in this direction. Okay, and what's going on? It's going from y equals 0, which is the x-axis, to y equals square root 2x minus x squared, which is going to be the upper part of the semicircle. So I'm going from y equals 0 to y equals this thing. All right. So the trick for this one is that, what is the trick? Okay, so I'm going into a polar integral. The trick is the really, figuring out what the heck the formula is. And this is one of the standard ones I mentioned earlier. So I know it's r equals b sine theta, or whoops, r equals b cosine theta. It's this guy. All right, so I'm going from r equals 0, which is this point here, to r equals, whatever, b cosine theta. In this case, it's 1, 2 cosine theta. Okay. So r goes from 0 to 2 cosine theta. And then the other hard part is figuring out the theta values, right? So it's not from 0 to 2 pi. It's not even from 0 to pi, because the truth is, to sketch out just the top hemisphere, you're going from 0 to pi over 2. Okay. If you don't remember that, you kind of have to go back and think about this thing, this r thing, and the r theta plane. So r equals 2 cosine theta has amplitude of 2, 2, 1, 2, and then it goes like that. And then when you draw that in the xy plane, you're going to have two sort of helper circles, and then we could add some guidelines if you want. So I'm starting out at 2. Usually have that little ruler thing to help me, but I don't have it. And then it's dying down to 0 at pi over 2. Okay, so from here to here, it's going, I put it in a different color, it's going like this. Okay, and that traces out the upper hemisphere of this circle. So a lot of people would put 0 to the pi or 0 to the 2 pi, and they would be wrong. It's 0 to the pi over 2. Okay? Okay, so then on the inside of the integral, we need x and y. X is equal to r cosine theta, y is equal to r sine theta, and then dy dx is r dr d theta. Okay. So we had 3 r's, so r cubed. So this equals the double integral of r cubed, cosine theta, sine theta, dr d theta, from 0 to 2 cosine theta, 0 to the pi over 2. Okay. And that would be your answer. Okay, just setting it up. So let's look at the next one. Evaluate the integral. It may be necessary to switch the order of the integral. That's number 8. 0 to 2, and then 0 to 2, and we have x square root of 1 plus y cubed dy dx. Okay. So if you try to just plain old integrate the thing with respect to y, you're going to be stuck right off the bat, because I have no clear idea on how to integrate the square root of 1 plus y cubed. Okay. I'd have to get, one of my PhD friends on the phone. So no, I'm not going to be able to do that. I need to switch the order to pull it off. In order to switch the order, I need to kind of figure out what the heck I'm integrating over. In this problem, oh, this should be an x down here, so not 0. It would be really easy if that was 0, right? That would just be a box. And for boxes, you don't have to pretty much don't have to do anything. You could just switch the order without affecting anything. But this one, we have to be a little more careful, going from x to 2. So let's take a look at the picture. The orientation is kind of our traditional orientation. My Riemann man is going in that direction. And I'm going from y equals x, which is this diagonal, to y equals 2. And I'm running on the x-axis from 0 to 2. Okay. So y equals 0 to y equals 2. And then from 0 to 2, this point here is at 2, 2. So it just must be this region here. Okay. All right. I need to change that orientation so I can pull off the integral. Okay. So I'll need to go from y, now x equals, right? So x equals 0 to x equals this curve, which is y. And then the Riemann man's going to run from 0 to 2. So not much of a big deal. Let's do it. So the integral, the double integral now is going from, we still have the same guts, right? So the same integrand. It's just now these bounds will be different. So I'm going from x equals 0 to x equals y. Okay, the formula for this is y equals x. Solving it for y gives you x equals y, right? So we got that top bound, our limit, and then the Riemann man is running from 0 to 2 on the y-axis. And hopefully that'll allow us to integrate this thing. Okay, so here we go. The integral of this with respect to x is only going to affect this element, so it'd be x squared over 2. And then there's a 1/2 you could pull out. So I'm going to have x squared times square root of 1 plus y cubed evaluated from 0 to y, and then we have dy, right? Okay, so that's going to work out marvelously. I'm going to plug in y for x and then subtract, plug in 0. That will be 0 for the second term of that difference. So I have 1/2 y squared times the square root of 1 plus y cubed. And then I just have dy. So that'll require, I can do it, but it's going to require a u sub, right? So I'll have to go u is 1 plus y cubed. Then du is 3y squared dy. So dy is equal to du all over 3y squared. So this will become then, in my new variable, 1/2 integral y squared times square root of u, but I'll write that as u to the 1/2, times dy, which is now du all over 3y squared. And so I can remove the y squares. I get another constant factor of 1/3. And if you pull that in front, you're going to get 1/6. Okay? And then you have the integral of u to the 1/2 du. And then integrate that thing, and you end up with 1/6 u to the 3/2. Right? So u to the 1/2 plus 2/2 is 3/2 times the reciprocal of 3/2, which is 2/3. And then we need to remind ourselves to evaluate once we back sub. I'll do that. So 1/6 times 2/3. 2 over 6 is the same as 1 over 3. So I get 1/9 times u, which is 1 plus y cubed, now to the 3/2 power. I need to evaluate that from 0 to 2. Okay. So I'll have 1/9 times difference, right? So 1 plus 2 cubed. 2 cubed is 8. 8 plus 1 is 9. So I have 9 to the 3/2. And then minus, plug in 0. It won't be 0, right? So it's 1 plus 0. So 1 plus 0 is 1. 1 to the 3/2 is 1. Okay. You can evaluate this part. 9 to the 3/2 is the same as 9 to the 1/2 cubed. Right? And 9 to the 1/2 is the square root of 9. That's 3, and then 3 cubed is 27. So I have 1/9 times 27 minus 1, which is 26. In other words, 26/9. Okay. All right. So what else we got? Evaluate the integral by converting to polar coordinates. Okay, so this time we actually have to evaluate the thing. 0 to 3, and then 0 to square root 9 minus x squared. And my integrand is x squared plus y squared to the 3/2 power. And then I have dy dx. Okay. All right. I need to figure out the region that I'm integrating over. And this looks fairly simple. It looks like it's just a semicircle. It's going from y equals 0 to y equals square root 9 minus x squared. So it's a semicircle, upper hemisphere of the semicircle with radius 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so I'm going from y equals 0 to y equals, the Riemann man is in the traditional orientation. So y equals 0 to y equals square root 9 minus x squared. And then he's running on the x-axis from 0 to 3. So it's not the whole hemicircle, it's just half of it. Okay, well, look, I need to transfer that into polar coordinates. This is r equals 3. We'll give you the equation that we need. And remember, the Riemann man, when you go in the polar coordinates, is now doing a circular dance, right? He's running around collecting little sectors of circles for his Riemann sum, and he's going in a circular rotation. So the bottom curve is below him. It's right here, and then the outer curve is right here. So on your inner integral for the r, the dr part, you're going from 0 to 3. Okay? And then we have x squared plus y squared is just r squared. And then r squared to the 3/2 is r squared to the, so r squared to the 3/2 is equal to r to the 6/2, which is r to the 3. Okay? And then there's another r from the r dr d theta. So you're going to end up with r to the 4th inside here, dr d theta. and I'm going from 0 to pi over 2. Okay, so from 0 to pi over 2. Right, so then I'm going to integrate the r to the 4th. It gives me r to the 5th over 5. You can pull out the 1/5 if you want. And I'll have 0 to 3 d theta. 3 to the 5th is like 2 something, 243. So factor that out. I looked at my notes. I don't have that memorized or anything. 243 over 5. So it'd be, 243 minus 0, so just 243, and then you can factor out the constant, right? So it'd be 1 d theta. And then integrate that with respect to theta, so it's 243 over 5 times theta, evaluated from 0 to pi over 2. So that will just be 245 all over 5 times pi over 2 minus 0, which is equal to 245 pi all over 10. I bet 5 goes in the 245. Oh, it's 243, sorry. See, I have no clue what 3 to the 5th is, but there it is. See, I have to get on the horns of my PhD friends, right? They probably know. Yeah, I'm having a mood today. Sorry. So let's see what's next. Number 10, we're going in the surface area. It's 243 over pi again. Not 245 over 243 over pi over 10. Okay. Number 10. Let's see what's going on there. What do we got? Surface area, right? So f of x equals 3 plus x to the 3 halves. A long journey to get the sort of integral that corresponds to it, but the deal is it'll just be the double integral over whatever region you're worried about of the square root of the partial with respect to x squared plus the partial with respect to y squared plus 1 dA. Okay, so you just, after you understand, where it comes from, and it comes from basically, I mean, what? This thing is finding the little tangent planes, the area of the little tangent planes, and then summing them all up over this surface here. Okay, this surface is pretty easy because there's no y variable, but let's take a look anyway. So the region R is a rectangle with points 0, 0, 0, 4, 3, 4, and then 3, 0. Okay, so let's look at our region 0, 0, 0, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, and then 3, 0. So it's this box to integrate over. So that tells you your limits on your integral. So I'll have integral, and boxes are always easy, and let's put our orientation in this direction. So dy dx, and then we need the square root of whatever in there. So he's going from y equals 0 to y equals 4, and then he's running from 0 to 3. And then inside here, partial with respect to x, right? So that will be the derivative of 3 with respect to x is 0, the derivative of this power rule. Bring down the 3 halves. X to the 3 halves minus 2 halves is 1 half. Okay? And then Fy, because this has no y's in it, you could just consider these both constants. And the derivative will be 0. So you're plugging this squared plus 1 squared into here. So you'll get 9/4 x to the 1 now, and then plus 1. Sorry, I have to smush that in there, and then plus 0. But at the end of the day, that's your integral. Okay, let's look at another one. This time we actually have to evaluate the integral. Okay, so number 11. Find the area of the surface again. So f of xy is 24 minus 3x minus 2y. So it's just a plane. And we want to know the area of that plane over top of the first octant. So R is the first octant. And to kind of figure out the region we're integrating over, maybe want to draw a picture in the XY plane, right? So if you let z equal 0, that will tell you what it looks like in the XY plane. So when z is 0, I'll have 2y equals 24 plus minus 3x, right? And then divide by 2, so you get y is 24 minus 3x over 2. So 24 halves is at 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then it's x-intercept. Let's see where that is. So that would be 3x over 2 equals 24. So x is 24 times 2/3. 3 goes into the 24. 8 times 2 will give me 16. I mean, really? All right, whatever. So is that right? 3 goes in, 24 is 16. We have I think I made a mistake on my test. Oh, it's 24 halves right here. Sorry. Well, yeah, okay. That's 8. All right, so 1, 2, 3, 4, 5, 6, 7, 8. There's our line. This is our region. First octant means you're going to be in the first. It's basically what you see when you draw your x, y, z plane, right? So it's the part that's kind of, you know, the house part. This region and enclosed by these planes. Okay, so this kind of room right here, and over top of the first quadrant. Okay, and okay, so hopefully that's clear what it means by the first octant. You know, it's kind of hard to describe that with my limited artistic skills. Okay, so anyways, we're integrating over this thing, and I need my double integral, and I need to evaluate it, and so I'm going to need the partial derivatives. Partial with respect to x will be just -3. Partial with respect to y is -2. And then we have the integral, the double integral. So if your Riemann-man is going in this direction, he's going from y equals 0 to y equals this 24 minus 3x over 2. And then he's running from 0 to 8. And then on the inside of the integral, it's square root of this squared plus 1. So 3 squared is 9, plus 2 squared is 4, plus 1. 9 plus 4 plus 1 is 15. So square root 15, or is it 14? Oh, jeez, sorry. Square root 14. That's what happens when I try to do things in my head. Okay, and then dy dx. So you could factor out the square root 14, no problem there. And then we got a double integral of dy dx. So with respect to y first, I'll end up with a y here from 0 to 24 minus 3x over 2 dx. If you plug this into here, you'll get just that minus this into there, which is 0. So you're just going to get this. So it's equal to square root 14 of the integral of 24 minus 3x over 2 dx. And then you factor out the 1/2, right, and put that in front. So you get the square root of 14 halves times the integral of 24 minus 3x dx. Okay? And then this will equal square root of 14 all over 2 times the integral of 24 is 24x minus 3x squared over 2. And then I'm evaluating from 0 to 8. Okay? And 8, what did I do wrong? I factored out the 1/2. Okay. So it's going to end up being 48 root 14. Okay, just hopefully you can take my word for it. I assume you know how to evaluate one of these things by now. Okay, let's leave it at that and move on. Next, we're working with triple integrals. Okay, so number 12, evaluate the triple integral. 0 to x, 0 to 1, 1 to 4. And on the inside, we have 2z e to the negative x squared, and then dy dx dz. Okay, so evaluate, right. Start with the innermost one first, and then work outwards. So double integral of this thing with respect to y is just going to be 2yz e to the negative x squared evaluated from 0 to x dx dz. And then we have the double integral. Plugging in x, I'll get 2xz e to the negative x squared. And then I plug in 0, it'll just be 0, so minus 0, you don't have to write it. And then I have dx dz. For the next part of the integral, you're going to have to do a sub. So let u equal negative x squared, and then du is negative 2x dx. I think I'm going to split the video in half here, because it's just long, and my computer will hate me if I don't. So I'll have dx equals negative du all over 2x. Okay. And do your substitutions. So you have double integral of what? 2xz e to now the u power times negative du all over 2x. Okay, and then dz. Right? Negative 1 over 2x times 2x is going to just give you negative 1, so I could factor out a negative. Then it's double integral of z e to the u du dz. And then you can integrate z, so that would be z squared over 2. Oh, whoops, you still have to integrate the e to the u, sorry. So negative integral z e to the u, the integral of e to the u is e to the u. And then you have to evaluate it once you back sub dz. So that would be negative integral z e to the negative x squared minus, you got to be a little bit careful. This time you actually have to subtract. So minus e to the, all right, so first I have to back sub. Sorry, let me just back one thing at a time, right? Back subbing, I get e to the negative x squared. Then I can evaluate. So from, what do we have now? 0 to 1. And that's where I have to be careful. It's not just going to be putting in the 1 and then this will be nothing, right? It's going to be z, and I lost my negative. There's a negative in front. Z times e to the negative 1 minus e to the 0, which is 1. Okay, so that's an easy mistake to make. This whole thing then becomes a constant that you can pull out in front. And then distributing this negative into this e to the negative 1 minus 1 will become 1 minus e to the negative 1, right? And then integral of z dz. Integral of z then is z squared over 2. So I'll have z squared over 2 times this constant, 1 minus e to the negative 1. Evaluate from 1 to 4. Okay, so then I have 1 minus e to the negative 1 all over 2. And plugging in 4 for z squared is 16. Plugging in 1 for z squared is just 1. So I'm going to be left with 15 halves on the outside times 1 minus e to the negative 1. And you just leave your answer like that. That's good enough. Alrighty then. Set up the region, set up the triple integral to find the volume of the solid. Do not evaluate. Okay, so let's take a look at that character. This is number 13, or maybe I should split the video. Yeah, let me split the video. Okay, I'll see you in the next video.